Okay, how can we tell about stars? It's all in the light. So interestingly, it's all about quantum processes happening at the atomic level within our stars, wherever they are and going on. I should say those that are breaking down the quantum stuff, so when we go beyond white dwarfs, they're off the bottom of this chart. It's nowhere in here. So we're looking at the most of stars which are mainly in that main sequence. And this really is revision from last year. So a quick bit of a heads up and a reminder, we know that atoms, all atoms basically have levels of energy, quantized levels of energy. Electrons can only exist at these certain amounts of energy. Thinking at GCSE version as the idea of shells, but actually it's a bit more complex than that. So what we've got is a section, and the reason to do this is it's all about how we measure the light that's coming from these atoms that are inside the stars to then give us a story of what's going on. So all of this is done is lab work, and by using that understanding from lab work we can then decode the clues from distant stars. So this is one of the key areas of astrophysics. So, quick reminder on this. There we go. Hydrogen, for example, which obviously is one big example because we have the ideas of stars basically based on hydrogen. So, how do we get energy from it? Well, what happens is we can give them a certain amount of energy, we can excite them by heating them, so we'll have electrons at all kind of levels jumping up and down, jumping up in atoms when they're heated, and effectively as they fall back down they lose that potential energy and give it out in the form of photons, pure energy. So the kinetic energy these have gained by being heated means that they can jump up to a higher potential energy. So that is why, to link in the last chapter, why we've got these negative values. So if we can keep jumping up until they reach zero potential energy, in other words, that kind of activation amount of energy is to get them to jump up to this level. Anything left over means things happen, the electrons fly out. However, below that is what we're interested in, smaller energies, and that's where they're falling back down, and to do that they give out these photons. So from our notes last year we know that it's all about the change in energy. Okay, so whatever we've got, energy 2 minus energy 1. Okay, so the difference, subtract the first one from the second one, and this will go to the frequency of the light emitted. Okay, now just remember, for light and photons, it's fairly low energy for most of the stuff that we're looking at, so it's electron volts. So if we were to take the example of this one here, for that to happen, then what we have is change in energy of minus 3.4, okay, which is where it ends up. So that's our second one. In this case, notice the arrow going up, so this is excitation. Subtract minus 13.6. I'm already well ahead of you in the maths there. So that needs 10.2 electron volts of energy given in for that to happen. Okay. Now within stars, which are full of hydrogen and helium, because they're being fused and so on, this process is just as important as this one. Okay, so stars give out light, and because they're heated, they're dropping from all kinds of levels, so they give out a whole wide range of photon frequencies, so a range of colours. However, the hydrogen in the cooler parts of the star will absorb some of that energy. For example, photons given out by the middle of the star, and that will cause electrons to jump up, and that will absorb those photons. So we end up with energy being absorbed by the outer gas, as well as energy being given out by the gases within the star itself. So the key thing is that usually for what we're going to look at, we're thinking about the gas in the outside of the star. And we're just assuming that basically the inside is a perfect black body radiator, giving out all frequencies of light. So, linking back in with gravity, we've got a bit of a link going on there. However, within what we're doing here, if you've got this de-excitation, again, phrases, things are falling to the ground state, okay, and assuming it's not ionized, they will just fall back in. So as it de-excites, then what we have to do is emit that radiation. So emit the energy as a photon. Okay, a fixed packet of energy. Just pick it up. So that is electromagnetic energy. Okay, and there's enough of them, they form rays, radiation, etc., etc. So if we are linking this together and reminding yourselves about electron volts of energy, then if we have this one here, so for example falling from energy level 3 to 2, then in this example E3 minus, E2 is the one minus E3, because that's where it's started from. You're going to end up with minus 3.4, again subtract minus 1.5, so effectively electron volts, that is, we're going to get minus 1.9 electron volts of energy. Minus means you're giving the energy out, okay, rather than taking it in. So, not much use on its own. We need to use that idea of W equals QV as your equation. So, volts, charge, give you the energy in joules. Okay, so that's the one that you're after for using E equals HF. So, we're going to just convert that, and you just say, well, minus 1.9 times, of course, 1.6 times 10 to the minus 19. So that's your charge of all of your electrons. However, it's not about the electron, it's about the multiplying factor. So it's a multiplying factor in this conversion to get you to a very small amount of energy, which I think comes out as 3.04 times 10 to the minus 19 joules, as you can guess. If you do that, E equals HF goes to a frequency of 4.59 times 10 to the 14 hertz. Okay, please notice again 3 significant figures, because these are all 3 significant figures. That on your data sheet is 1.60. Okay, so they're all 3 significant figures. And just to remind you, it's emitted. So that's the process of giving out the light. The crucial bit in the first place is how do you get it excited in the first place? You have the heating of the atom. Okay. And we should say excitation of, if any of the atoms, but heating of the atoms, which is a bit random, I should say. It's a bit hit and miss. How high will they go? Where it depends. It just depends on how much energy is absorbed, and if you use some heat to jump up one electron, that heat can still then excite another electron. So it's there's lots of randomness, as I say, in that whole process. Okay, from the fusion process. We have the other big one is that we can have an incident particle, because particles are being shot out all the time. So, excuse me, incident particle, whatever particle it is, colliding with an atom, with the atom. And so what happens there is you basically, or the electron, it doesn't really matter, I should say. It doesn't really matter, but some, and this is again a crucial idea, just in terms of they could twist this in a question, some of its kinetic energy will then be given to the electron. Let's say it's passed on. And then the bit that matters for us, for our analysis, okay, so that's kind of background, that's how stars go out light. This one is crucial in that it absorbs energy from photons emitted by core and, you know, further inwards, core atoms of the star. Okay, and that's important because of where we're going for this. So lab work, black body radiation gives us this idea of continuous spectrum, so all the colours of light. This again is visible light, 400 700 nanometers, infrared, ultraviolet, and so on. If we heat different gases, we get out these unique fingerprint emissions. Okay, so depending on the size of the gap, you get a different frequency. Bigger the fall, the bigger the frequency, because that's energy. So these unique fingerprints give us that, okay, and we can measure those from their wavelength. So effectively, as hinted at there, we know that my preferred version, but the version you'll need is the one of wavelength. So speed of light divided by wavelength is of course the same as frequency. Okay, so by looking up at stars, if we can spread out the different frequencies, the different wavelengths like this, then we can actually start to see which gases are contained within the stars. So that's how we know the chemical makeup of stars. Okay, and it links into this whole idea of light being given out at these different frequencies. Now, I'm going to let you work these out, a little bit of practice. Okay, so this is worth doing. Find us what the 6 emissions are. C, D, so let's do that. Okay, you can do it on a whiteboard, but classic questions, you're going to get loads of those. The crucial bit, and this is where it links in. Here, this is what you get if you take your continuous light from the star and then you surround it by a cooler level, a cooler layer of hydrogen and helium that's not being fused at the moment because it's on the outside of the star, still falling inwards due to gravity. That will of course be cooler. Okay, so as the core of a star is millions and millions and millions of degrees of heat, of temperature. We're only looking around about 6,000 Kelvin on the outside. Relatively cold, maybe cool is perhaps a better word. However, let's put the outer gases of stars are cooler than the core. And so basically they're excited, they excite the outer ones. We don't give out light, but we excite them by absorbing energy from photons coming out. And so, yeah, absorb photons from the inner layers, the inner gases. Okay, what that means is that you end up with photons missing because they're being absorbed. So you end up with dark lines in your spectrum. So the dark spectrum shows absorbed frequencies or absorbed wavelengths. Okay, and that is, strange enough, called an absorption spectrum. So how do we know those? Because they match up with the exact same frequencies of the emission spectra. When you heat a gas, those are the lights given out, those are the colours given out. That's done in a laboratory. If we then match them up and go, oh, we have the same spacings at the same colours, then we know that these are the same chemical elements within it that are absorbing that. And so, as I just said, in terms of completion, when the atoms absorb the photons, electrons jump up. Let's put in, of course, excitation rather than using the phrase jump up. Excitation by the same amount. Okay, so certain amount of energy, let's just put in of energy, which gives us those characteristic fingerprints. That you can see if we can split the colours up, and the colours can be split up. We've done it last year when we were looking at the double slit, and then we demonstrated this as well, so diffraction grating. So if you take your telescope and stick a diffraction grating on the end, what you'll find is you'll get that constructive interference forming very distinct lines. And again, what I've done for you at no expense spared is I've actually given you some of the colours. So photograph of what you'd actually see from the stars. So you've got your bands of colours, your first fringe, your second fringe, first and second to the left. You've got your whitish light from your star, and what we're seeing is that range of colours that fits in with a certain equation, just like we practiced last year, but very definitely in this topic. So just remind you, light is in module 4, so that's in the second paper. However, this is module 5, which is in the first paper. Questions like this tend to come up in paper 3 as well, because they're a mixture of topics. Okay, so in here what we're getting on is that idea where we can give out the spectrum, and so we get the excuse me, jump over. Oops, I lost my thread there. So we jump over from what we've just had, and what we can get is finding out the different wavelengths, and from that we can use the equation of n lambda equals d sine theta, okay, where d is distance between between the slits, okay. Now, warning on this, which will fill in, you are not normally given the spacing between the slits. You'll get how many slits, how many slits are in a millimetre. Okay, so it might say 400 slits per millimetre. Okay, 400 gratings per millimetre. You want the distance between them. So again, it needs to be in metres, which I'll put in there because it's an SI unit, of course, to make it all work, because that will give you a wavelength in metres. But basically what you need is D equals 1 over N, where N, capital N is number of slits per metre. Okay. Theta is the angle. It's the angle between these. So your central bright fringe is straight on. How far round to measure your first fringe, your second fringe, and so on. So this is really a curve, and you're measuring the angles between those. Okay. So let's do it this side. Bum 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 bum. That's your theta. Okay. N is the order of the fringe. So this is what you've got here. So N, is it the first fringe, or is it the second fringe, or the third fringe? The 0th fringe is the one in the middle, the central bright fringe. Again, notice that's the colours are being spread out. because it varies with wavelength, but the more they're spread out, that's because you're multiplying the number there, so you're getting a bigger angle there between the different colours, different wavelengths. However, you still get groups of colours, so you get the full spectrum there, full spectrum there, full spectrum, full spectrum. If you get further out, they tend to overlap. In the middle, where you have zero fringe, you won't be able to work anything out because there's no angle, but it does mean you've got all of the wavelengths. So that is all colours of the spectrum. It's worth pointing that out, because guess what comes up a lot in questions? Okay, at CBF, central bright fringe. Okay, so those are the main things. Lambda is of course wavelength, so we've got those two kind of key things to get us that angle. So from that we can measure the wavelengths, we can get all the things we can need by literally looking at the angles, and even without measuring, you can shine them on the wall and you can see what colours are missing. There would be gaps in that for where the absorption spectra is. Now, just be wary. Sometimes, again, just as a kind of a mathematical exercise, they'll ask you to see if this was your grating here and your fringes were all spreading out in different directions, how many would show up on a screen or a spectrometer in a full 90 degrees from the central bright fringe. Okay, so if this is your light coming in here, they might ask you to work that through. So maximum diffraction you'll get is 90 degrees. It's just a case of rearranging that. Okay, so if you needed to do it, how many fringes would you see? N lambda equals D sine 90, which is times 1, etc., etc. So N equals D over lambda. Now, don't forget that is the number here. So actually, total fringes seen is seen equals 2 times n, okay, because there's two sides, 1, 2, and your central bright fringe. Okay, so that's worth putting that is each side. Okay, so the mathematics and revision from last year's stuff, useful, not as big, not as important as trying to get your head around the next section, which is actually looking at not wavelength, but other things that we can measure from it, the brightness and so on. Okay, so to get us back to the Hertzsprung-Russell diagram, we need to think about its temperature and so on and so forth. Okay, how's that done? Comparing light from stars, to the actual the light given out by gases in a laboratory.